So today we will see another method of amortized analysis, which is called the potential method. In the last class we saw how amortization gives a better analysis. There, if you observe what we did for certain operations in the binary counting algorithm, we overcharged certain operation, like we paid 2 rupees for that, and for some other operation we didn't pay anything, that was undercharged. But ultimately the operations which were undercharged were paid from the money which we paid for the overcharge operation. So as if we are distributing the cost over all over the operations. So that is the main theme of the amortization. Here today we will see a formal method which is called the potential method for doing this amortized analysis. So this time what will happen, that the data structure of the algorithm will build up a potential. Okay, and this potential will be paying the cost of the operations. So as if the data structure is an object, it is building some potential on it, some charge. For certain operations it will build the charges, and for certain operations it will use those charges, it will use its potential to pay for that operations. Okay, that's the main theme over for this type of analysis. So let me just go over what do we mean by this potential method. Suppose Ci is the actual cost of, say, ith operation, and Di is the data structure after ith operation. Now phi Di is the potential of Di. Some charges, as if this data structure Di is accumulating some charge. Now let Ai, the Ai is the amortized cost. What is amortized cost? It is defined as Ci plus change in the potential, which is phi of Di minus phi of Di minus 1. So this is the amortized cost of ith operation. So this is just a definition. So look at the amortized cost. What it is counting? It is saying Ai is the amortized cost which takes into account the actual cost Ci plus the change in potential in the data structure, phi of Di minus phi of Di minus 1, due to the operation ith operation. Now again let me repeat. Now this change of potential, suppose it is positive. Suppose it is positive, what does it mean? It means for this operation you are building some charge on the data structure, or in another sense you are overcharging the operation, because your actual cost is Ci, but you are measuring a little bit more, so you are overcharging this operation. But for some cases this might be negative, the potential may be negative. So in that case you are undercharging that operation, because you are taking in that case the actual cost minus something. But what is happening, this charge, when it is negative, how it is coming into the picture? Because from those operations where you are overcharging them, it is accumulating that charge and paying it for this particular operation. Okay. Now the main property of this definition of amortized cost is this: if I take amortized cost over all the operations, so I take the summation of Ai, that is the amortized cost over all operations. Say we have n operation, I is equal to 1 to n. Then this is, by definition, I is equal to 1 to n Ci plus phi of Di minus phi of Di minus 1. and this is again, if I manipulate a little bit, I is equal to 1 to n Ci plus phi of dn minus phi of d0, right, because all the other di's cancels out. Now if we choose, if phi is chosen such that phi of d0 is 0, so initially the potential was 0, and phi of dn is greater than 0. Suppose the way we have chosen the potential, suppose these two conditions are satisfied, then what do we get? Then we get this, that sigma I is equal to 1 to n Ci, that is the total actual cost, is less than equal to sigma I is equal to 1 to n what? Ai. And this is most important fact. Why? Now I know that suppose with this potential function, if I evaluate the amortized cost and take the summation over all the operations, all the amortized cost, I know the actual cost, this has given me an upper bound on the actual cost because of this fact. We are interested ultimately in the actual cost, but doing this, I know that the summation of all the amortized cost over all the operations is bounding the actual cost from above. So if we have a bound on sigma of Ai, it will also give a bound on sigma of Ci because of this. But I need to make sure that phi of d0 is 0, phi of dn is greater than equal to 0. In between, whatever happens, phi does not matter. Sometimes it will decrease, sometimes it will increase. Now let us see. Suppose we apply this technique to our binary counting algorithm. You remember the binary counting? Just let me go over it a little bit. It was something like this. There were several positions. Say we have this, and the next one was 0 0 0 0 1. Next one will be 0 0 1 0 0 0 0 1 1. 0 0 1 0 0. So it goes on like this. Okay, the algorithm was, suppose the array Ai contains the bit ith bit, then you scan the array from right to left, and as long as there is a 1, you make it to 0, and the first 0 you make it to 1 and stop. Then you will get the next number. Like here, first one is 0, make it 1, stop. The next one 1, you scan to the next, 1 is made 0, scan to the next, 0 is made 1. In this case, this is the first 0, 1. Now in the next one, 1 1, you make both of them 0, then the first 0 make 1. So that's the way it proceeds, the algorithm. And suppose we are counting up to n, so our goal was to estimate what is the total cost of counting up to n of this algorithm. And we have already counted it to be linear, order n, by that credit method. We are crediting some operation with ₹2 and we are crediting some operation, nothing. Now let's see. Suppose for this one, our potential function, suppose we define like this: phi of di is equal to bi, where bi is equal to number of ones in the string, or in the string is fine. So basically, here what is bi is 1 only. What is bi here? 2. There are 2 ones. Okay, that is basically the number of ones. Now let me define another one which is called ti. This is the number of trailing ones. Okay, what is the number of trailing ones? Basically, if you scan the string from right to left, the number of ones you will be getting consecutively. So here it is 0, here it is 1, here it is again 0. Number of trailing one is 0. Here it is 2. There are 2 trailing ones. Here it is 0 again. So that is the value of Ti. There is a difference between Bi and Ti. Okay, you can see that Ti guides the computation because that many ones you have to make 0 to get to the first 0, which you will make it as 1. So suppose we define the potential as say Bi, potential of this data structure. Data structure means basically you can take the array as the data structure, some object. So phi of Di is equal to Bi. Okay, first let us see whether we have satisfied this condition that phi of D0 is 0 because we started from here. Phi of D0 is 0 and phi of Dn definitely will be greater than equal to 0 because some ones will be present in that number. So phi of Dn is greater than equal to 0. So we have satisfied these two conditions. So if we can add the amortized cost now, we should get an upper bound on the actual cost. So let's see what is the amortized cost of the ith operation. So what is the amortized cost of ith operation? According to our definition, A of I should be C of I plus phi of Di minus Di minus 1. This is my amortized cost by definition. Now what is Ci? Actual cost of the ith operation. In terms of Ti, it is Ti minus 1 plus 1, right? Because there were Ti minus 1 trailing ones which you converted to 0 and this 1 is accounting for the last 0 which you made 1. So this is the actual cost of the ith operation. Now let us see what is the cost for the or what is the change in the potential. So we want to measure what is phi of Di minus phi of Di minus 1. Now this is definitely by definition this is equal to Bi minus 1 by definition. Now what is Bi in terms of Bi minus 1? Bi is Bi minus 1 minus Ti minus 1 plus 1. The number of ones which were present, you subtract the trailing ones because those ones you made 0. So they cannot be present in Bi anymore. So you subtracted it. And then you made the last 0 to be 1, you add the 1. So this is the total value of the ones in after this operation, ith operation. Minus Bi minus 1 for this. Now this definitely gives you 1 minus Ti minus 1. Can you see here that the potential change can be negative now depending on the value of Ti. Potential change can be negative. So what is Ai now? Ai is Ti minus 1 plus 1 plus this potential change which is 1 minus Ti minus 1. So this gives you 2. So this is the amortized cost of each operation. And if I sum over all the n operation, so sigma of Ai is definitely less than equal to 2n. And I know the actual cost, that is sigma of Ci, is less than equal to sigma of Ai. So here this potential change is taking care of everything, all the other costs. Sometimes this change will be positive when Ti say is 0. For some operation it will be 0. In that case it will be positive. For most of the time it will be negative. But everything it is distributing over. The positive ones will go and pay for the other ones. Okay, now let us, so now you have an idea of this potential change method. Now let us go to this advanced data structure which is called Fibonacci heap, where I will be using this concept heavily. So what is a Fibonacci heap? Before I tell you what is a Fibonacci heap, the structure itself, let me tell you what are the operations it supports. The operations are, because any data structure first you have to specify what are the operations it is meant for. Efficiently it can support. Like binary search tree, probably you will say search, insert, delete, all these are efficiently carried out by a binary search tree. So here make heap is one operation. You have to make one heap first from scratch. Then insert is another operation in it takes the heap H itself and it inserts an element, say X. Then minimum is another operation which returns the minimum value over all the keys currently present in the heap H. It just returns the value. Then there is another operation meld, is like merge basically, H1 and H2. What it does, it takes one heap H1, another heap H2, it merges these two heaps into a single heap. Then there is another operation delete, delete min H. Now in this case what is happening, you extract the minimum from the heap. This time not only return the value, there is a difference between minimum H and delete min H. This time you return the value and delete it from the heap. And there is another one which is simple delete, delete Hx. Basically from the heap H, delete the node X. We will see that we will be giving the pointers, because this is not a search tree. This Fibonacci heap is not good for search. Like heap is not good for a search structure. You cannot search efficiently in a heap. Now there is another operation which is very important, decrease key Hx delta. What it does, it takes the heap H, it decreases the key value of X by delta amount and restructures the heap. So this is the decrease value. If you go back to the heap structure, there also you can have this. Given a pointer to a node, you decrease its value, then you restructure the heap. You go up or down depending on how you have constructed the heap. But here is the difference. Make heap takes how much time? So here I am listing the time, but this is amortized time now, not actual time. Make heap is order 1. Insert Hx is again order 1. In constant time you can insert an element in the heap. If you remember, in the original heap you cannot insert an element in constant time. It takes log n. Minimum of H, it takes only order of 1 again, is constant time. Then merging two heaps is again constant. It's like a magic data structure, everything is constant. No, there is two operations where it pays. This delete min takes order of log n, and delete Hx also order of log n, because basically delete min and delete are same, they are the same operations. Delete will use the delete min operation. And now the classic part of this data structure is the decrease key is order 1. In constant time, amortized time, you will have decrease key. All these operations, if you go back to your heap structure, you cannot like decrease key cannot be in constant time. Even insertion cannot be in constant time. Delete min is order log n, which is fine. But here we are gaining in this insert decrease key. Here suddenly the amortized time is much less. So if I have say n decrease key, I have spent total time not more than n. But in the heap structure, if you have n decrease key operation, you must have spent at least n log n in the worst case. So that's why this data structure is better than the plain heap data structure or even binary search tree. Any data structure you know of, this is much better for all these operations. You can try to see, suppose a simple data structure like arrays, stacks, linked list, how can you, or binary search tree, heap, how can you support all these operations? And you will see total cost will be much less for certain operations for this Fibonacci heap data structure. That's why this data structure is important, that it can give you better time bound, and it is also important because it teaches you how to use the potential function. This is a perfect example where the analysis, where the data structure has been built depending, actually keeping the analysis in mind. So let's see what is this data structure now. Before I tell you, there is another motivation actually why this data structure was invented. We'll see in graph algorithms, this particular data structure, which is the Fibonacci heaps, will give you better algorithms for different problems. Simple data structure will give you a log n factor, but suddenly if you use the Fibonacci heap, the same algorithm will give you without log n factor. So what is the structure of this? The structure of this Fibonacci heap is as follows. It is a collection of heap ordered trees. I will tell you what is a heap ordered tree. You know it already. So it's a collection of heap ordered tree. What is a heap ordered tree? Heap ordered tree is again a tree where each node has the key value less than equal to all its children. That's what it is heap. The binary heap has only 2 children at most. In this case, now one node can have more than one child. But the property is that its value will be less than equal to all the key values in its children. Just like the heap, mean heap structure, we also have each node has its value less than equal to the 2 values in its 2 children. So here is an example of a heap ordered tree. Say I have 1 here, 3, 5, 6, 10, 12, 7. So this is a heap ordered tree. Every node has less than the values of its children. Now, as I told you, Fibonacci heap is a collection of such heap ordered trees. But how we represent these collections? Before I go over the collection, let me tell you a little bit more which this data structure use on this each of this heap ordered tree. Like if I take the previous heap ordered tree, it will be represented like this: one node, then all its children will be linked by a doubly linked list. Okay, so there is a doubly linked list. Both ways it goes. Similarly, it has 2 children. They are doubly linked list. This has 1 child. This is pointing itself, and there is no sibling, so this. Also, each node has all the pointers for its children. And each node has a parent pointer. Each one points to its parent. So this is the representation of the previous tree which I just drew. So this is the tree. This is one heap order tree. So this is the way we will represent it. All the siblings of one node will be connected by a doubly linked list. Why doubly linked list? Because in the doubly linked list, if a pointer has been given to a node, deletion of that node from the list is order 1 operation. Otherwise, it's not an order 1 operation. If it is a single linked list, you cannot delete one node in order 1 time. because there is no way you can get the pointer to the previous node. But if it is doubly linked, you can get the pointer to the previous node immediately. So that's why everything is doubly linked. Now, such heap order trees in a Fibonacci heap, as I told you, it's a collection of heap order trees. So I'm just drawing one Fibonacci heap here, which is a very trivial one. So suppose I take one heap order tree, so 1, 7, 9, so this is, and say this is another one, say 10. So this is one heap order tree I have taken. I may have another heap order tree, say 3, and it has only one child, say 5. I may take another one which is the single node itself. Okay, yes, it is circular, suppose. Now what will happen in the Fibonacci heap, we will represent all these heap order trees in a collection. All the roots of the heap order trees will be linked in a doubly linked list. So all these roots are now connected with the doubly linked list. So this is the Fibonacci heap now. So Fibonacci heap is a collection of heap order trees where all the roots of the heap order trees are linked by a doubly linked list. Not only that, we also, how do we have a pointer to the Fibonacci heap? It is through a pointer which is called mean of H. So suppose H is the Fibonacci heap here. Mean of H will point to the root which contains the minimum element among all the roots. So between 1, 2, 3, this is the minimum, and there is a pointer mean of H pointing towards that. Okay, what are the fields, major fields which are used for each node? So a single node will have, first of all, 4 pointers. What are those 4 pointers? One is for parent, children, then left sibling, right sibling. Alright. Actually, I should not say 4 pointers because children, it can have many children, more than 4, but 4 categories of pointer, I should say. So 4 categories of pointers. One is the parent pointer, child pointers, then right sibling, left sibling. Then we have one real, which is the key value. Then we will see, this will be used later, one bit which is called the mark bit. Some of the nodes in our operations will mark. Some of the nodes in the Fibonacci heap will mark. So how do we mark? Using this mark bit. Okay. As we proceed, we will see what is the use of this marking. And there is one integer which will tell us the degree of the node. What is the degree of the node? Like in this case, the degree of this node is 3. That is the number of children it has. So that's also kept. So these are the major fields which are kept in the structure of a node. Okay, now let us start the operations on this data structure. I have not told everything about the Fibonacci heap. As we go along with the operations, we will slowly acquire something more about the Fibonacci heap. Okay, for the time being, let's assume that this is all we have with the Fibonacci heap. So first, the simple operations. What are the simple operations? I should not say simple operations, simple manipulations maybe. One thing what we will be using in those operations is this is a sub operation, what I am just telling you. This will be used, which is called the linking. So what do we mean by linking? Given 2 heap ordered trees make root with bigger key the child of the other root. So suppose here is an example. Suppose I have a heap order tree and its root has value say 1. I have another heap order tree whose root has a value 3. The linking of these two means that this is made the children of this one. And of course, you have to take care of this doubly linked list and all those things. You have to properly do that. So this is the operation which is called linking, and this definitely is ordered one time, worst case. It's just manipulation of some couple of pointers. You just make this one as a child of this and make its parent pointer point to this. And probably you have to take out the circular list of its siblings or the children of 1 to take into account 3 in it. But that also can be done in constant time since we have the doubly linked list for the children of 1. So this is actually ordered one time. So this operation, when I say linking, this sub operation, it means exactly this. There is a reverse operation which is called the unlinking. It is just the reverse of the previous one. What does it mean? Suppose we have several heap ordered trees. They are in a circular list, the roots. And suppose this is T1, this is say T2, and there is say Tk. So suppose I want to unlink the tree T2. So what does it mean? You just take it out. So suppose there is a pointer given to this root. You just take it out from the circular list. Unlinking means you just unlink from this circular link. So the picture will look like now, say this one, T1, and this is say Tk, and basically you will have this. So T2 is gone. So in this case, what is the time complexity of this one? Again, order of 1, because it is only manipulation of some couple of pointers. So this is linking, the other one is unlinking. Okay, we will also use merging of 2 cycles. Merging of cycles, another sub operation. So suppose we have a cycle of nodes, that basically under them there is a tree. Another cycle of nodes. You want to merge these 2 cycles into a single cycle. So what do? We just cut open this somewhere. It does not matter where. You cut it open and cut this one also open and join say this one here, then it becomes a single cycle. Okay. So merging of 2 cycles, basically you take 2 doubly linked lists and merge the 2 into a single linked list. So this is how much time does it take again? Order of 1. Okay. So these are the very simple manipulations will be, yes. These are the very simple manipulations which will be used in implementing those particular operations which I just mentioned. Okay. Now, as I told you, this entire data structure uses some potential function. So what is that potential function? So let us now concentrate on potential function which we will be using for this data structure. Okay, let Z1, Z2, Zn be the sequence of operation. I don't know which operations are there. It is any of one of them. I listed some operations like Z1 can be insert, Z2 can be insert, suddenly Z3 is a delete min, Z4 is an extract min, then again Z5 may be a make heap, Z6 may be a merge, one of those. This sequence of operations. Now let Ti of H is equal to the number of roots in the root list. What is the root list? Basically the doubly linked list which is linking all the roots into a single link. That is the root list. So number of roots in the root list, that is Ti H after the operation Zi. So when you did the operation Zi, after that whatever number of roots are there, that is called the Ti of H. There is another quantity Mi of H. I cannot tell much about this one now because this will come into picture towards the later part of this explanation of this data structure. But for the time being, assume some of the nodes are marked, as I told you earlier also. Some of the nodes of the Fibonacci heap are marked. So this MIH is number of, you will see that why this is used and how this is used. Number of marked nodes in H after the operation Zi. So these are two definitions, TIH and MI of H. Now I am going to define what is the potential function. Potential function will be using this Ti of H and Mi of H. So here is the potential function definition. Pi is equal to, okay, this is Pi basically phi I. I am just using Pi now. Pi is equal to Ti of H plus 2 Mi of H. Now you may question at this point, why did we choose like this? The answer to this, because it works. Okay, but when somebody invented this, he did not go in this one way direction, like he chose this one then designed the data structure. No, probably somebody has chosen initially something else, it did not work, he adjusted the function, again he adjusted the function, then finally probably this one was the one which was obtained and it works. And particularly why it is 2, you'll see at the end of the analysis that this 2 works. If you don't put 2, the analysis does not work. It does not compensate properly. So 2 is necessary there. Now let us see. First of all, let us verify whether it satisfies, this potential function satisfies those two conditions. What is P0? P0 is before any operation. So any operation the heap is empty, there is nothing. So it is 0. There is no root node, there is nothing marked. So P0 is 0. Now as we have defined Pi is equal to TIH plus 2 Mi of H, definitely Pn is going to be a positive quantity. There is nothing negative here. So Pn must be greater than equal to 0. So these two conditions are satisfied. So if we do the amortized analysis, take the sum of all the amortized cost, it gives an upper bound on the actual cost. Now let me go over some of the trivial operations of that list. Now the first operation was make heap. So what do you have to do? Make heap means you have to make a heap out of scratch. There is nothing. So the step is create basically nil pointers. So suppose you have declared the data structure, so you initialize all the structures. No node, nothing has been created. Probably mean H, what you will do in this operation, mean H will point to nil. There is nothing else. Okay. So what is the cost of this one? 1, order of 1, because in this case the potential change is 0, and the actual cost and the amortized cost is same, because no root has been created, nothing has been marked. So potential change was previously 0, now also 0. So it is 0. So order 1 is actual cost, order 1 is also amortized cost. This is a very trivial operation. That is the operation 1. Then there is the second operation, minimum of H. So what do you do in this case? Return the minimum key, because min H is pointing to the minimum key. That's it. So what is the change of potential in this case? After this operation, pi minus 1, what is this? This is 0, because it did not affect the number of root, did not affect anything marking. So it is 0. So again actual cost is equal to amortized cost, which is order of 1. Okay, let us stop for this, up to this one now. In the next lecture, what I will take up the other operations. We will see those operations are much more interesting. These are very trivial ones. In the next lecture, I will continue over other operations.